Hello, this is Nicholas from Silicon Chip Publications, and today I'd like to quickly go over our upcoming April 2026 issue, which goes on sale Monday, 23rd of March, which is around the time this video should go live. So here's the cover of the magazine, which features a few of the projects in it. You can see the Calliope amplifier, stepper motor driver, and this Pico SDR shortwave receiver, which I've done a video about recently. I'm not going to go over every single article in the magazine. I'll just look at the most important ones. Switching to the contents page now, you can see there are 8 main feature articles. History of Intel Part 3, which is the end of this series. Power Electronics Part 6 on DC to AC converters. This article on whole house thermal logging. So basically, Julian built a house and he incorporated temperature and other sensors throughout it and a logging system so that he can see how it's the temperature of various parts changes across the day and throughout the year. And then we have an article on a vintage Tektronix oscilloscope. It's an analog oscilloscope that's still relatively new but old enough that it needed restoration. And the interesting thing about this article is that he goes into quite a bit of detail about why electrolytic capacitors fail when they get old, how to detect it, and what to do about it. And then we have the projects, this shortwave receiver based on the Raspberry Pi Pico that I've gone over before in detail. I'll briefly touch on it this time. This stepper motor driver, which has some unusual features in that it can essentially allow you to control a stepper motor similar to a regular motor, in the sense that you apply DC voltage, and the higher the voltage, the faster the motor will turn, and the polarity will control the direction. Of course, stepper motors work quite differently from DC motors, but it essentially translates that. And it can also act as a DCC receiver, meaning you can use a stepper motor to control a model train, which is an interesting idea as well. Then we have the Calliope amplifier, which is an update of an amplifier we published in 2021, which was very popular, called the Hummingbird. And what's great about this is it's a very compact board, inexpensive, easy to build, but it can still deliver up to 100 watts, and it operates in class AB, so it's quite good quality. It's a hi-fi amplifier. And this update provides some minor improvements, but it also greatly widens the part selection that can be used. And that's important because often a lot of the parts we design into amplifiers will be obsolete a few years later. So this way you can still just select a different part if the existing part becomes obsolete. And then we have the final project, a simple Micromite based music player. So the Micromite is a PIC32 that's programmed with software that allows it to run basic code. And in this case, it's also attached to a touchscreen. So the touchscreen with the PIC32 can be connected to this DF Player Mini module, and it makes a very easy way to play MP3 files through a speaker. And we have some other articles here. We have Mailbag, which is letters from our readers. Circuit Notebook has a couple of interesting circuits. Serviceman's Log, I will go over that briefly, about repair stories. Ask Silicon Chip, more letters, but this time asking questions with our answers. And that's pretty much it. So let's have a look at the first article, History of Intel Part 3. So obviously we've had a couple of articles already on the history of Intel from the early days up to the present. And this article now is going to look at Intel's current products and their future products. So over the last few years, they've released this new technology that lets them combine multiple chips into a single chip using what they call tiles. And so it shows you here how they now have compute tile, which is the CPU effectively, SoC, which I guess has a lot of the system functions, a graphics tile, which is like an onboard GPU, and an IO tile. So this lets them mix and match different technologies and also build a much bigger chip than they could fabricate monolithically. And here's showing the complexity of a modern CPU. Another image here showing how the tiles are combined. And also this fairly important advance they have now, backside power delivery. So instead of power and signals all coming in through the top and having to make their way down the layers of the chip, now you have the signals coming in at the top and the power coming in at the bottom. And that can provide quite high improvements in efficiency and other benefits. Here it shows how they're combining dies in this 3D fashion, stacking them on substrates and so on, and how some of the vias, how you can actually stack more than one die on top of each other. This shows the new FinFET technology that they're using. We talk a bit about Intel's GPUs, which are relatively new and starting to become competitive. Some of the people who were CEO of Intel over the years some of their major fabrication plants. They have a lot more than that, but this is the large ones. We talk about Optane, which is now obsolete, but was a very interesting product. Phase change memory, and a very old Intel discrete graphics card. Some of the other things that they've bought companies that make chips that are used in drones and so on. Quantum computers that they're working on. They've also developed USB and other technologies related to that. And then this AI board that they've developed recently. Moving on now to the next article, we have, I've talked about this in detail just about a week or two ago. It's a software defined radio based on the Raspberry Pi Pico. And because it uses software techniques, this is the RF board. It's quite simple. It's basically just tuning and then amplifying the RF signal. And then this digital multiplexer is controlled by the Raspberry Pi and acts as the mixer, the RF mixer. And we have a dual op amp here that basically recovers the I and Q signals that go to the Pico. And then the Pico is able to recover the audio with various modulation schemes and send it to the speaker through this amplifier. So a nice, simple design, relatively speaking, and quite a capable radio. It's based on software developed by a third party, but the author of this article developed the board, the hardware for it. There's the list of parts that you need. So we have the PCBs, but you'd have to get the rest of the parts yourself. And there's also this optional external screen, which can provide a waterfall and spectrum display. Moving on now to the power electronics article. So this is coming up towards the end of the series. It's part 6. I think there's another 1 or 2 parts to go. And this is an interesting series because it's a blend of academic and practical information. So we have some formulas in here. It's not super high complicated mathematics, but we do have a few Greek letters and so on. So there's a bit of analysis here, but there's also just a very practical side of showing example circuits and waveforms, and even actually testing products to show how they work. So this is talking about DC to AC conversion, which is obviously very important in things like motor drives, solar inverters, that sort of thing. And he's showing how single phase and 3-phase AC can be generated, how it's filtered to form a sine wave. And then we're talking about harmonic elimination, which is able to remove a lot of the components of the square wave that's producing the sine wave signal. Hysteretic current control, which is another method for recreating the sine wave. And then we get into space vector modulation, which is quite an advanced technique for generating motor control waveforms. The analysis of that and how to actually sequence the switches to produce the waveforms you want as easily as possible. And now he does an analysis of a DC to AC converter, looking at how do you calculate the losses that will occur in the semiconductor devices. And that's obviously important for things like sizing the heatsink, the fan, working out efficiency, things like that. So that's quite a useful exercise there of looking at both the fixed losses and the switching losses, and how the switching losses vary based on frequency, because often you want to go to a higher frequency for various reasons, such as less ripple on the output. But then you also have increased losses, so you have to take that into account. So moving on now to the next article, we have our stepper motor driver. As you can see, it's a pretty small board. It has a microcontroller, a couple of ICs on the back that contain the main motor driving transistors and control circuitry, a bridge rectifier, and then a few other bits and pieces. Here's an example of a stepper motor that can drive, or there's a whole range of them here. And here's an oscilloscope grab of the drive waveform. So this supports microstepping. I believe it's 256 microsteps. And we also have a kit for this. So as I mentioned earlier, it can be used in a model train situation, but you can also just use it as a general stepper motor driver if you just want to control a stepper motor. The nice thing about it is you just have to feed a DC voltage. It can work with AC or DC voltages, but if you use a DC voltage, it can actually monitor the amplitude and the polarity of it, and it can use that to then determine how fast to drive the motor. And I believe it supports motors up to about, where does it say here, 0.5 amp. So small stepper motors, but of course it's a small board. Here's how to wire it up. And you can also have, there are a couple of LEDs you can attach that will, by default, it will show you forward or reverse, but you can also change that. and then how to configure it if you're using it for model railway with DCC. Now the next article is about the home environmental logging. So he shows you here, this is his logging setup with these two Pico log units, and he has a screen that can show how the temperature, insulation and things like that vary across the day and throughout the week. And he talks quite a bit about how he's put sensors in the slab, which was problematic because water was, even though he'd sealed them, water still got in. So there's some tips if you're trying to do this sort of thing, what to avoid, and also how he's modeled how his house will behave with respect to sun heating it over the year. So different times of year, you'd expect different angle of the sun, different duration. It's going to affect which rooms get hotter and so on. And by adjusting the positions of windows and doors and things like that, you can optimize it so that it's not as hot in summer, it's not as cold in winter, that sort of thing. So that's quite interesting and useful, I think. He talks a bit here about the climate where he lives, and you could compare that to where you live and see how different it is. Where I live, for example, it's hotter, so you'd be more concerned about keeping it cool in summer, but in some places, it gets very cold in winter, so that might be more of a concern. It's quite interesting to see these detailed logging results. Here you can see how the sunlight varies. So obviously there's a cloudy period here. You can see a dip, and then some of these other days there are passing clouds that cause dips and so on, and how that affects the temperature. It's quite useful, especially if you're going to build a house. Some more logging there. And then moving on to the next article is the amplifier. And he shows here why it's important to choose the right transistors. There's quite a dramatic difference here in the recovery from clipping based on whether you've used the recommended transistor or not. Here's a photo of his test rig, and you can see he's comparing units using different transistors, different resistors. I believe, in fact, this is actually the old versus new design, because you can see the coil is orientated differently. Here's a list of some of the different transistor options. So you have looks like about 8 different options for the output transistors, a couple for the driver transistors, although they're related devices. They're very similar, but they're widely available and they're not likely to go away anytime soon. And then for the voltage amplification stage, which is quite critical, he has over 10 different options, although some are hard to find now. Part of the point of this design was the observation that for the VAS transistor, most of the good options now are in surface mount packages. So he's designed the board so it will accept either through-hole or surface mount devices here. So there are some good choices like the BF720, BF722, which are easy to get and do a good job, as long as you don't mind soldering a surface mount device. If you really don't want to, then there's quite a few through-hole parts that can be used if you can get them with varying degrees of success. But the important thing is that there are options there. So whatever you can get that's recommended will work. Here are some load line curves showing how it's not going to blow up driving 100 watt loads using various different output transistor options. And he also shows with the dotted lines the protection curves, because this does have load line protection, so that if you overdrive it, it will actually shut itself down, partly shut itself down. It will limit itself to avoid damage. And here he shows the measured performance and how it varies depending on how you run the wiring. So there's quite specific instructions on doing that. Here shows how you should route the wire through the module for best performance, because you get magnetic field cancellation from the current running through these wires. Here's the circuit of the amplifier. It's pretty standard, but there are some details that have been considered, some important things, like this transistor here that prevents Q14 from going too hard into saturation on negative clipping. Here's the board. That's the original layout, and this is the revised layout on the right. You can see they have, for example, one of the changes is the Q4 and Q12 have moved closer to the output transistors, and that allows him to keep the tracks a lot shorter, which improves the performance slightly. But as I said, the main thing is this option for Q14 to be a surface mount device, because many of the good options these days for the voltage amplification stage are in SOT 2223 packages. So it's good to have that option. Here's the parts list. Altronics are doing a kit like they did for the original Hummingbird. but the parts, we sell the PCB and the parts are all relatively easy to get, so you could put it together yourself from separate parts if you wanted to. Moving on now to the music player article. As I mentioned earlier, it's a very simple device. So this here on the right is a pre-existing design, the Micromite LCD backpack, which basically just connects this PIC32 with a simple power supply to a touchscreen via this header here. And then we connect the DF Player Mini to that, and you have a music player or an audio player. It's very simple to build. This is the add-on board, which doesn't have very much on it. That just connects to the backpack, and that has the music player module, which uses a micro SD card to hold the MP3 files. Here's where you can drill and cut a small box. He used one from, I believe it came with cotton buds, to attach the screen through a hole in the lid and so on. Cut out for the speaker for the USB port. There's also this board here, which has, instead of it being an add-on to the existing backpack, you just build it from scratch. So you can see how simple it is. The chip, the module, the headers for the touchscreen, a USB socket, and then a scattering of a few parts, not much. Speaker connects to Con 6. There's the parts list, and you can see the unit he's built here into this box. And it's a very simple project, pretty good for beginners. Useful. You can use it to play sound effects or messages or music, that sort of thing. He recommends it for playing soothing noises when you're going to sleep, which is another good use. So a nice simple project there. And then we have Serviceman's Log, which is about repairing stuff, and he goes into quite a bit of detail here about kettles and why, in theory, a kettle is a very simple device, and if anything fails, you should be able to replace it. But in his case, his very expensive kettle has a very expensive part that really shouldn't be. This is the thermal switch here. In a cheap kettle, it would be a few dollars. For some reason, on his kettle, it's like $100 to buy a new switch, which is ridiculous. But a lot of equipment is going that way. And then we have some more repair stories here. This heat gun, which basically he managed to put the switch into an intermediate position, which burned it out. There's not much left, but he was able to repair the board and get a replacement switch and fix it for a lot less than a new heat gun. This electric cooktop, I think it's an induction cooker. The switch mode chip on there failed. You can see the charring on the board, and he talks about how it works and how he was able to fix it. I believe he swapped the board, but he was also able to repair the old board. So he has a spare now, and then an electric fence repair. So some useful information, and it's entertaining, but it's also gives you ideas of how to fix things. And then we have our Vintage Electronics article this month about the analog oscilloscope. And as I mentioned earlier, what's interesting about this is the amount of detail he goes into, talking about why the electrolytic capacitors fail, what are good choices to replace them, and what damage they can do when they do fail. So, for example, I believe there's a photo here showing how, yes, here we go, the electrolyte leaked out of the bottom of this capacitor and it became acidic. It increased its pH to around 9, it should be closer to 7, and that damaged some of the tracks on the board. You can see the liquid here. You can see here the corrosion that it's caused that he had to fix. And he talks about things like, replacing these capacitors early before they leak so that they don't damage the board. What capacitors should you buy to replace them? Which ones are going to last a long time? Not surprising, he recommends brands like Nichicon, which are known to be good, although interestingly the failed capacitors were made by Nichicon, so that's no guarantee, obviously. He also talks about X2 and Y capacitors, which are usually either ceramic or plastic film, and some of them can fail too. He talks here about these reefer capacitors. Their casings crack and they burn up, and what you can replace them with that don't have the same problem. So that's the April issue, goes on sale around the time this video will be released. You can buy it in a newsagent. You can subscribe via our website. There's also online PDF subscriptions. And there are other articles in here I haven't gone over. But that's the major articles. So I hope you've enjoyed that. Thanks for listening.